Thank you guys all so much for coming out to the USACO Bronze Problem Review. I assume all you guys are in bronze and hoping to move up the ranks. A little about me. I'm the director of USACO with Breakout Mentors. Breakout Mentors is a tutoring group dedicated to making students, specifically high school or middle school students, progress up the ranks of USACO. So if you guys are interested, please do check that out. It's a picture of me. We also do other things. So Breakout Mentors also does programs for machine learning, iOS development, Unity, whatever you really want to get your hands on when it comes to programming. So if you guys are interested, please feel free to reach out. But with that out of the way, we're going to hop into the problem review. Now, before I start, I want to make sure you guys are get all your questions answered. So if you have any specific questions, please feel free to DM me or stop me in the presentation. Just raise your hand or send me a direct message and I'll check the chat. Make sure that those questions get answered, because this is definitely not an easy contest. So with that in mind, let me pull up the questions real quick. Let's see what we got. That's what this is. I'll share this thing. Okay. Can you guys still see? Thumbs up? Awesome. Okay. So I'm going to try to annotate on top of this problem. Sometimes it helps me to see the problem while it's going on. So, okay. So typically we have some kind of cow-related problem, and that is the case this time. Bessie is not paying attention in class. And so there are some number of times that she's falling asleep in her classes, designated with this array here. AI for of size 10 to the fifth, and each of these values can be 10 to the sixth times. Now Elsie wants to make it so this list of numbers representing the number of times that Bessie falls asleep in each of her n classes is all uniform, right? So Bessie wants to transform this array to make all the numbers the same. And the way she can do that is say the array was 1, 2, 3, 4, 5, as we showed here, is by combining values inside of the array, right? So if she combines 2 and 3, for example, we'll end up with an array looking like this instead, where the 2 and the 3 are just added together. Everyone following so far? Okay, awesome. So the idea is, what is the minimum number of times that Elsie needs to actually modify this list in order to end up with a totally uniform list of numbers? You guys want to help me out for the first test case? So let's say we have 1, 2, 3, 1, 1, 1. How do we make this list all of one number? Or if you could put in chat what that number is first, that would be awesome. You guys help me out? Awesome, cool. Abhinav, you want to come in online and tell us why it's 3 here?
Yeah, so basically the last 3, you have 1, 1, 1. You can combine all those to become 3, and then towards the left of 3 you have 1, 2. You can combine that to be 3.
Perfect. That's exactly right. So we combine this 1 and the 2 here to get 3, and then still a 3 here. And then we combine all these 1s. So we might start with combining these 2 to get a 2 here and 1, and then we combine these 2 to get all 3s. Does that make sense? Everyone good so far? Okay, awesome. The question is, how do we do this efficiently, right? As always is the question. So how do we do this efficiently? Well, one observation we can make is that every time we do this modification, it's not actually changing the total sum of values inside of the overall array, right? So whenever we do these combinations here, so in the last example, when we combined, say, the 1 and the 2 in this sample case, the total sum across all the values, even after we combine the 1 and the 2, is still going to be the same as it was before. So the sum in this list, can someone tell me what the sum of the values in this list is? So that's this list right here. Awesome, thank you. And what's the sum after we put the 2 and the 1 together. Awesome. Perfect. You guys are good. Okay. So no matter how many times you do this modification thing, the total sum of all the values is going to stay the same, right? And this is very important. Now, we want to end up with a list where all the values are the same, right? So we want to end up, we'll say B is the end value. In the previous case, B was equal to 3, right? Because we ended up with 3 3s. So if we want to know what B is in this case, right? Let's say our new problem is just figuring out what the value is that we're trying to condense down to. What are the possible values of B? And this is a tough question, right? So say we know the total sum of our array is 9 in this case, right? What could the values of B possibly be? Yes, exactly, Abhinav. So for those of you that didn't fully get there yet, B has to be a factor of the sum. So we have to be able to split the total into a bunch of B chunks, right? So for example, here, our total is 9. The total of the values in the array is 9. So we need to end up with chunks of some factor of 9. So the factors of 9 are 1, 3, and 9. So if B is 1, we're just going to end up with a bunch of 1s. Right? If B is 3, we're going to end up with 3 3s. And if B is 9, we're just going to end up with 1 9. Right? Let me write that out. So if B is 1, we're going to end up with 9 1s. If B is 3, we're going to end up with 3 3s. And if B is 9, we're going to end up with 1 9. Now, all these are proper divisions of some list that sums to 9. Can someone tell me which of these lists are actually possible given the list we started out with? So if we start off with 1 2 3 1 1 1, which of these lists can we actually do? Can anyone else give me the answer or explain the answer? I want to make sure everyone's on board. Abhinav, great work though. And if anyone's stuck at all right now or confused, please let me know so I can rewind a little bit. Very happy to rewind. I want to make sure everyone's on board. I'm going to wait for someone to tell me which ones other than Abhinav. Again, feel free to put questions in the chat if you guys are lost here. I'm sorry if you guys are, I don't want you guys to be lost right now because we still have a little bit more to go for this problem. Yeah, of course. Okay, so I'm gonna rewind a little bit. Thank you, John. So the idea is we have this list, right? And whenever we do a modification to that list, where a modification is combining two numbers, right? If we combine two numbers, it doesn't change the overall sum of our list. And this is the key fact, right? So if we start off with 1 plus 2 plus 3 plus 1 plus 1 plus 1, where this is our original list, the sum of these values is equal to 9. And then if we combine any two of these values, right? So say we combine these two, we're going to end up with something that still sums to 9. Is that okay? Does that make sense? Okay, wonderful. So I guess moving past that then, if we want all of our values to be uniform, which is what Elsie is trying to say, she wants to make all the values in our list the same, right? In that case, we want to make all the values in our list equal to some variable we'll call b. We'll say b is the value that we want all of the variables in our array to be equal to. Does that make sense? Okay, cool. And we want there to be some number of b's, right? There's some number of b's. But we know the sum across all of the b's that are left has to be equal to our original sum, right? Because all we're doing is doing modifications to get to a bunch of b's, right? So then what we can observe based on that is that if we have some number, we'll say there are A B's, then our total sum is going to be equal to A times B. So A times B in this case is going to be equal to 9. Is that okay so far? Okay, cool. Genoa, is that okay? Awesome. Okay, wonderful. Thank you guys. Thanks for sticking with me. So if we know A, B equals 9, and these are both integers, that's going to tell you something about the possible values of B here, right? So what can A and B both be? What are the possible values of B here? And the answer is B can take on any of the factors of 9, right? So for example, B can be, or sorry, not for example, that means B can be equal to either 1, 3, or 9, because these are the factors of 9, right? If B was equal to 7, there's no way we could have a list of any number of 7s that sum to 9 still, right? So we can't have 1 7, because that doesn't equal 9. We can't have 2 7s, because that equals 14, right? That's not 9. And we can't have any more 7s, right? B can't be equal to any number other than 1, 3, or 9, which are the factors of 9. Does that make sense? Okay. Okay, wonderful. Is everyone else doing okay so far? Give me a thumbs up. Awesome. Okay. Cool. Okay. Now we're past the hard part. Now the question is, if B can only be the factors of 9, or alternatively, the factors of the total of our array, right? Because it's not always going to be 9. In this case, we have 7 as our total, right? So if we know that B can only take on a number of values equal to the number of factors in the sum of our array, that limits what we might want to try, right? So let's say we're just trying to figure out what B is, right? What's one thing we can do? We know that B can only take on a factor of the sum of our array, right? So our solution could be to try all B's. And surprisingly, this actually works out. There aren't too many factors of the sums of A. And that's partially because A is limited. I think it says, yeah, the sum of all the values in A is at most 10 to the 6th, which means the number of factors of A is actually quite small. It's small enough to iterate over all of them, right? So we can actually just figure out what the sum is. We can compute it. We'll say our sum is T, right? Just kind of confusing here. We'll choose a different one. We'll say S is our sum of our input, right? And we want to know all the factors of S. Now we don't know what we're going to do with those factors yet. We don't know what we're going to do with B yet, but let's first try to figure out what the factors of S are. Can anyone tell me what a fast way is to find all the factors of S, or a semi-fast way? It is an O of N operation. Can you give me like a specific, like step-by-step real quick? You can unmute too, or just general idea would be good.
Yeah, just iterate through every number up till n, and then like if its mod is 0, add it as a factor.
Awesome. Yeah. So for everyone who didn't catch that, all we're doing is iterating through all the values 1 through whatever S is, and we're checking, right? We're saying, okay, is S divisible by our number? We'll say it's potential B. We'll say B question mark. So in this case here, we'd say, okay, is 1 a factor? Does 1 divide 9? The answer is yes. Does 2 divide 9? The answer is no. Does 3, or sorry, wait, I'm doing this the opposite way, my apologies. Does 1 divide 9? Yes. Does 2 divide 9? The answer is no. Does 3 divide 9? The answer is yes. Does 4 divide 9? No, and so on and so forth, right? Now, for those of you that aren't familiar, the way to check if something divides something is using this modulo symbol. I'm not sure how many of you guys are familiar with this, but in Java or C++ or whatever programming language, even in Python you're using, you can say 9 modulo, say 4, and this is going to be equal to 0 if, or sorry, this is not going to be equal to 0. But if you divide 9 by b, this is only going to be equal to 0 if b divides 9. You don't have to know how that works, but basically the way we check if something divides something is using this modulo operator right here. Does everyone know this, or is this a new thing? I was confused when I saw it in this problem because I'm not sure that everyone in bronze knows about the modulo thing. I sure didn't, but okay, cool. But basically we just check if the sum is divisible by whatever number b is, and we check b from 1 up to our sum s. Wonderful. Okay, cool. So now we can figure out all the b's really, really fast. Let's say we make a list of b's, right? What do? Let's say in this case, I figured out, okay, b equals 3 is an option, right? What can I do now? Does anyone have any ideas? Abhinav, good point. You can actually do that in Overden. It's a bit of a side note, sorry. But we can talk about that later if you want. Just want to keep this moving for now. It's awesome. Does anyone know how we can maybe figure out, if we know what b is, if we know what number we're trying to combine to, how we can end up with that number? Sorry, it's so dark in here. Any ideas? You don't have to be right. This is a really hard contest again, so feel free to toss anything out there at all. Keep track of a counter. Interesting. What kind of counter? Largest sum, and ooh, I like that. Okay. Genoa said if the largest number is b, that's a good first start, right? What happens if the largest number is greater than b? It's a really good idea. It cannot be b, exactly, right? So if one of these numbers is 4, suddenly we know that we can't condense it. We can't get anything smaller than 4 as our final number. And so we can eliminate b, right? So that's a really good first start. What's the next thing we want to check? Or sorry, not the next thing we want to check, but like how else can we progress this forward? Some continuous elements. I like that. Okay, cool. That's a really good thing. And it goes back to what you said about the counter, right? So this is the next step, right? First we check. You guys actually nailed it here, you guys together. So really good job. First, we want to check if the largest number is less than or equal to b. That's very important, because if it's not, then we can't do this thing. And then we want to go across and kind of sum the adjacent or continuous elements, right? So like Abhinav said, we start at 1. We're like, okay, we know we got to combine 1 with something at some point, so it might as well be the next element, right? We're going to say, okay, we're going to say 1. It's not equal to 3 yet, which is b. So we're going to say b equals 3. So we're going to combine it with the next element. We're going to add 1 to 2. And we get 3. We're like, oh, shoot, we're good. We can stop adding numbers to this, because otherwise we would exceed b, and we don't want that to happen. So we can kind of move on to the next element. We see the next element is already 3. So we kind of move past that. We portion it off again. And then we do the same thing for the next one. We're like, okay, 1 isn't 3 yet. So we add the next number to it. Okay, it's still not 3. We're going to add the next number to it. And we're like, okay, that's 3. And this works, right? We're good to go. And we can actually just do this, right? It's not too bad to just kind of keep iterating through. And if we hit B, just kind of resetting our counter and going back from there over and over again, if that makes sense. So for example, say we had an extra, it's a good example of this. So we're doing a 3, b equals 3, but there's a 2 here instead of a 1 at the end. So what would this look like? We'd say like, okay, we check, we add 1 to 2. Okay, that's good. We get 3, that's good. Okay, like 1 plus 1 is a little bit less, so we still got to add the next element. And we're like, ah, shoot, we've gone over b, right? So we can't really do anything. We know that b actually fails in this case, right? And the reason why we have to keep adding values is because these ones have to combine with something in order to eventually be equal to b, right? We have to condense these ones inwards. So we have to add them since they're next to each other, but we can't do that here, right? Because if we kept adding values, we would end up adding this 2, and that would make it exceed B. We can't pull in values from in front of the 2, unfortunately, because we can only combine adjacent elements. And also, we can't pull in values from before, because remember, these values are already equal to 3. And so pulling from it would mess up the previous chain as well. Does that make sense? We need to add a case for the final. Yes. So we do need to check at the very end, potentially, if we end up with the correct amount of elements. However, this is not if you do it smartly, you don't have to do this. And the reason is, remember that we checked if our total sum can be divided by B, right? So if we get all the way through and none of the cases exceed B, we actually don't even have to check if the last one is exceeding B or less than B, because we know it divides evenly, which is kind of interesting to think about. Does everyone kind of see that solution? Are there any questions about it? I know I went through that a little bit fast. But basically, if we have B, the idea is we can check. That's why I lost 2 test cases. Wait, sorry, what do you mean by that? Do you elaborate? I'm very curious.
Yeah, no, in the official thing, I lost some test cases because maybe I didn't have like a proper edge case for this algorithm.
Oh, interesting. Okay. Would you mind telling us your algorithm for this?
Yeah, I did it like some sort of like, I did it with like 2 pointers. Like I had like a pointer at the left and then a pointer at the right. And then like I summed up till when the pointer was equal to the whatever B we are checking. And then if it's equal to like the number of tries is just going to be the right pointer minus left pointer. And then I moved the left pointer up and then I kept checking.
Gotcha. So you went through kind of like similar to what we did where you had a left pointer. Did the right pointer start all the way at the end of the graph?
No, the right pointer also starts at this left pointer.
Got it. Okay. And you kind of iterated up through until you got to 3.
Yeah.
And then you move the left pointer up too. Okay. Yeah. So that's exactly what we're doing here, right? Where we move this left pointer up here, and then we keep going from there. Yeah. There's a little bit of added complexity with having that comes with adding multiple pointers. So I'm sure that might have been where the small error came, but that's interesting. I wonder if the edge case was like not dividing properly or something like that. But anyway, that's cool. I'm glad you almost solved the problem. That's super cool. But yeah, okay. Since we can now solve for a given B and see if we can combine this array using the given B, can anyone tell me what our algorithm looks like, or what our final algorithm looks like, I guess? So sorry, that's a bit of a step, but basically we know that the number of B's is limited. We have small number of B's, and we can check if B works for any of these B's, right? And we can actually do this in linear time. The reason we do that is because if we're just going across and summing elements as we go, we're not like kind of going back and computing things over. We're just doing one pass through the list is the idea. So if these 2 things are true, can anyone tell me what our algorithm might be overall? Besides Abhinav? Sorry, Abhinav, you're doing great. I just want to make sure everyone's included right now. Everyone's on board. Is anyone confused? Does anyone want me to backtrack? I know that part was a little bit fast. O of n. Oh, shoot. I'm sorry. Okay. Thank you. Sorry about that. That's big O notation. It's linear is the idea. So what that means is we only do one pass through the array, which means we only check each element one time. And so the number of times we check elements is equal to, or approximately equal to, the number of elements in the list, which means our algorithm is really fast, right? So we can go through all these elements and figure out if B works in what's called linear time, where linear time is just the number of times we check things is about the same as the size of the list. Does that kind of make sense? The idea is like our algorithm is fast. Is that okay? Or did I answer your question? Okay, cool. Wonderful. So basically the idea that we combine these is we pick every single B and we check if B works for all of them, right? So we say, okay, for B equals 9, does this work? And the answer is yes, because we just keep a running sum all the way across until we hit 9, right? So we say, okay, is 1 plus 2 9? Not yet. Plus 3, not yet. Plus 1, plus 1, plus 1. And we're like, okay, we hit 9 and we're at the end of our list anyway, so we're good to go. We can combine all these numbers to 9, and we can do the same with 3. We can not do the same with 1, right? Because like John said before, we have elements that are larger than 1 in our list, right? And so our answer is, okay, it can be, B can be either 3 or 9. Which one do we want to pick? The lower one, exactly. We always want to pick the lowest one. Can you tell me why? Yes. If it's a large one, that means we need more partitions. Or sorry, that means we need more modifications to condense it more, right? So I told you at the beginning that we have some A, B's, such that A times B is equal to our sum. And if B is larger, that means the number of groups we have is smaller. And so the number of modifications we need to get to the smaller amount of groups is more, and we don't want that. So like John said, we need the smallest possible B we can get. And so we want to choose B equals 3 here. And it actually turns out that if we get B, right, so we know B equals 3, and we know S equals 9, right, that's our sum. Can we solve for A? What is A equal to here? Remember, A is the number of B's. S over B, awesome. Cool. So if A is the number of groups we have, right, and we're going from S elements to A elements, how many modifications do we need to get there? Where a modification, remember, subtracts 1 for the number of total elements by combining 2. So how many subtractions do we need to get from S elements to A elements? Help me out here. It's not obvious. It's the idea is if we have S elements, right? So here we have 9 elements, and every time we combine 2 elements, realize that's subtracting 1 from the total number of elements we have, right? And if we want to end up with A elements in the final list, so remember we want to end up with 3 3s in the first example, how do we go from 9 elements to 3 elements? Anybody? Or how many modifications does that take, I guess? Wait, am I doing this wrong? Hold on 1 second. Sorry, I think I might be confusing myself. My apologies. Hold on. I'm interpreting this incorrectly. Let me double check the number of modifications real quick. Yeah, so the answer is 3. That is correct. Yes, yeah. So these are the modifications you need to get to. But I'm wondering, I think there's a closed form for the actual number subtractions. Hold on 1 second. I think, why am I forgetting this? It was in the solution, so It's right here. Yeah, n minus r. That's totally okay. Yeah, anyway. So the idea is you can figure out the answer should be, wait, what is n here? Is anyone else, am I, oh goodness. Sorry, apologies. Anyway, you can either count it out by counting the number of times you do it in the algorithm, or there's some other way to do it, but it's blanking on me right now. I apologize for that. But like Jenna said, you can just count out the number of times we modify when we're finding b, right? So every time we iterate through and combine values, we can kind of keep a counter for that. So when we combine the 1 and the 2, we add them together, we add 1 to our counter. Well, we don't add anything to the 3, that stays the same. And then we add the 1s together. We do this twice, right? So we can kind of add 2 more tallies. And so we see the number of modifications we make is 3 here, and so on and so forth. Is everyone kind of okay with that? We're going to move on to the next problem now for the sake of time. But if you guys have any questions, feel free to stop me. And thank you for your participation so far. Okay. I think so I thought it would be s minus r, but for whatever reason that doesn't work out, right? Because we end up with 9 minus 6. Oh, guys, I'm so sorry. Okay. It's not s minus r. That's what I was trying to get at. The number of elements is equal to n, which is 6 in this case. And if we subtract 3 from that, we end up with the number of elements we want, right? So, goodness, I'm so sorry. Basically, if we have n elements that we start off with, right? So in this case, we have 6 elements here. We need to do 3 modifications, or 3 pairings, right? 3 subtractions to get down to 3 elements. So it's not going from 9 elements to 3 elements. It's going from 6 elements to 3 elements, which is why we end up with 3 here. In the second case, can someone tell me what a and b is for here? This is the last thing we'll do, I promise. So what are a and b in this case? Or the best a and b, I guess. That's proposed by a Silver student. Really? That's cool. 7 or 1. Awesome. Yeah. So our total is 7. Our b is 7. And our a is 1. Right? Now, since n starts off as 3, our answer is n minus a, right? Because we want to go from 3 groups, which is the number of elements in the very beginning, to 1 group, because a is a 1, right? Remember, a is the number of b's we end up with. So we want to condense this to 1, 7, just by itself, right? And we want to go from 2, 2, 3 to the 7, right? We're going to go from 3 elements to 1 element, which is a difference of 2. So we need to make 2 modifications. And so our answer is 2. I hope I didn't confuse you guys too much at the end, but I hope that makes sense. Can everyone give me a thumbs up if they're following pretty okay so far? Okay. Awesome. Okay. Wonderful. Thank you guys. This is my first time doing this, so I apologize. It's a little bit shaky, but hopefully we can go a little faster this time. Okay. So now we're going to photo shoot. So we get a little bit more interesting. This is a really hard problem. I wonder if maybe we can skip to this one. Let's do this one. This one's going to be fast, I think. So did anyone, first off, did anyone have any ideas for doing this problem that they were excited about or thought, was anyone able to do this problem, do you think? Solve this nice. Anyone else? Were people able to look at this problem? I know sometimes I get into the bad habit of always reading in the order that the problems are presented, which, by the way, I would highly, highly recommend always reading all 3 problems before you start solving anything. It significantly makes things better, because if you got stuck on question 2 or something like that, then you never get to read this question. I think this question is solvable, but like Abhinav said, it's not the cleanest thing to solve. Yeah. I think this problem was a pretty brute force implementation problem. And so I was not so happy with this problem. So I apologize to any of you that had to solve this, but yeah, that's pretty much how it went. But anyway, basically, we got these 4 wooden blocks. Each of them have characters on them, right? They got letters on them. So the idea is you want to try to combine these cubes together to make the given words, right? So it's a little bit confusing how the input is presented, but basically this first thing is the first cube. This represents, let's see if I can illustrate this. Sorry, my cube drawing skills are not so on point, but I'll try my best. Ooh, look at that, it's coming together. I'm a CS student, not an art student. Okay, and on one side, we're gonna have an M, and on the other sides, we're gonna have like maybe an O back here, and O on this cover. What type of math is this? Thank you very much. You guys are so supportive, man. Oh my goodness. But the idea is we have this cube, right, that has a bunch of letters on each side, and we want to use these letters to get all the words we want. So this is your first cube. Your second cube is going to have all O's on it, and your third cube is going to have an A on one side, a B on the other, then a C, a D, an E, and an F, right? So you end up with 4 cubes that you want to use to make these letters. Now, first off, what is the biggest possible word you can form with these cubes? Anyone tell me? How many letters can it have? 6, very close. How many cubes do we have? There's another question. 4, nice. So we only have 4 cubes, which means we can only have 4 letters in any word. And how many different letters can we have at each index, we'll say? So every word is going to be consisted of 4 letters, sorry. And how many, 4 letters, right? How many possible letters can we have in each index, right? So we got 4 indexes. There's some letter in each of these locations. How many possible letters can we have in each of these columns, so to speak? Anyone tell me? John, why you got it right the first time. It was the number you said the first time. 6, nice. It is 6. So we can have 6 possible letters in each kind of index, right? So the number of words we can form in total, if the order was set, let's say I chose the order of the cubes to be, this we'll say we'll label these 1, 2, 3, 4. Let me zoom in a little bit, make it easier. Safari is being uncooperative right now. Okay. Let's say this was cube 1, cube 2, cube 3, cube 4. Even now, oh my goodness. Wonderful. 1, 2, 3, 4. Wonderful. We got 4 cubes. Let's say that was the order of the cubes, right? So the first one's either going to be one of these letters, right? So the first letter of our word has to be M or O. The second letter has to be O, right? Because that's the only thing on any side of the cube. The third letter can be either A through F, any of those letters, and the last letter has to be one of these, right? How many possible words can we end up with? It's a little bit harder. Little math here. If we have 6 letter options over 4 letters, how many words can we end up with? You guys got this. I believe in you. 24, 1 is full of O. Gotcha. Okay. So we're saying 6 times 4 right now. Okay. Interesting. I think it might be a little bit bigger than that, unfortunately. And the reason is we're not just choosing, what am I trying to say? We're not choosing one letter. 4 to the power of 6. So close. So close. Wait, Oh no, it is 4 to the power 6. My goodness. Sorry. Goodness. See, even I make mistakes on this kind of stuff. My goodness. So the idea is we have wait. Wait, no, sorry. It is 6 to the power of 4. I'm terrible today. So for each cube, we have 6 choices, right? And we get to make this choice 4 different times. So the total number of words we can have is actually 6 to the power of 4, right? So we can choose any of these. I know there are only 2 letters in this first one, but basically if they were all different from each other, we would be able to choose 6 letters in the first cube times 6 letters in the second cube, 6 letters in the third cube, and 6 letters in the fourth cube. Just turn this well. Yes, yeah. So that's one way to think about it, Abhinav. There's also like permutations to worry about, but right now we're assuming we use all of the letters, right? So 6 times 6 times 6 times 6. Can anyone tell me what that number is? Anyone got a calculator handy or is really good at arithmetic? Anyone? I can pull up a calculator if you guys want, but I know you guys got a calculator in front of you. Thank you. Wonderful. Thank you, General. Okay. 1296. That's actually really small. 1296 is plenty to iterate over, actually. So we can actually try every single one of these combinations to figure out all the different words we can make, which is kind of interesting, right? It's a very, very interesting brute force case. But the one thing we're missing, or 2 things we're missing out on, and this is what Abhinav mentioned, right, is we might want to form 3-letter words, or 2-letter words, or a 1-letter word. And also, the order of these cubes isn't always like this, right? We might want to put this cube before this cube, or this cube before this cube. So there's some other variants that we need to consider, right? Besides just the letters we're using on each of these cubes. So if we want to consider, first off, the ordering of these cubes, can someone tell me how many possible ways we can order these 4 cubes? Each cube that solves the problem. It does for the words, or sorry, it does for the number of letters in our words, Abhinav, but it does not for the order.
It does, because like if the first cube can be 0,
Yes.
and then the second, third, and also you can get different combinations as well.
Let's say I wanted to make the word OM.
OM?
Yes.
Yeah, so then you would just like, wait, can you make the word OM? Yes.
Yes.
Wait, no. Mu, U, A, B, C, D, E, F, G. No, you can't make the word OM, right?
So you can actually put the blocks in different orderings.
Wait, no, but, oh yeah, you can, because like, you would just like, select the, like when you're going through it, you would just select, you would select null for this one, and then you would select O, and then you would select like M. Like if you go through all the, wait, let me look at my code. Let's see.
But the idea is you have to be able to consider not just the original ordering of the blocks, right? You need to find some way to say like, oh, we might want this block to come before this block, if that makes sense. Right? So we also need to consider not just which cubes we're using or which letters we're using from each cube, but also the orderings in which we want to put those letters, right? So can anyone else hop in? 24 arrangements, that's perfect. Good at math, nice. Okay. And 4 factorial is equal to, or sorry, 24 is equal to 4 factorial, which is, for those of you that don't know, 4 times 3 times 2 times 1. The reason this is the number of orderings is because we can choose out of any 4 to be the first cube. You've got 4 options here. After we choose the first cube, we have 3 options to choose the second cube. And then of the 2 we chosen, say we chose like these 2 to be the first 2 cubes. Now we have 2 options to choose the second to last cube. And of course, the last cube is already determined. Yeah. So that's another way to do it. It's a very clever solution as well. So 4 times 3 times 2 times 1, we have 24 different permutations, they're called, or orderings of the blocks. And since 4 factorial is 24, which is again very small, we can actually just try every single one of these orderings, right? So we can not only try all 1,296 different words, but we can also try all different letter combinations. We can also try all 24 different orderings of those letters. And for each one, this is the last thing, we can choose to remove some of them to get smaller letters. So how many different ways can we remove letters from this word? Can someone tell me? This is the last little math problem we have before this problem is solved. I'll label these. Someone help me out. 31104. Oh, this is not the product of these two values. The number of ways. This is a separate question. Sorry, John Hua. But what I'm asking is, how many ways can I like remove cubes? So say I wanted to make a 3-letter cube, for example. I need to remove one of these cubes and not use it, right? So say I wanted to make like MAU, for example. I would probably remove this cube, right? And I'd only use the remaining ones. So my question is, how many ways can we remove cubes, given that we have 4 cubes? The answer, for the sake of time, 4 choose 1. So that's if we want to remove just 1 cube. This is if we want to remove 2 cubes, we actually have a little bit more. Right, so the answer is actually 2 to the power of 4. And the reason is, for every single cube, we can choose to either keep it in or keep it out. Exactly. Right, and if we have this choice for all 4 cubes, so if we have 2 choices, we saw this before, you guys are getting like a combinatorics lesson now. This is awesome. We have 2 choices over 4 cubes, which means the number of total solutions we have is 2 to the 4th, right? So the total number of things we have to try is 1,296 times 24 times 2 to the 4th. And John Hua, can you tell me what that is? Oh, yes. What's the total of everything now, or the total product of everything? Awesome, 497,664. And I know this sounds like a lot, but this is actually reasonable to loop over. And so what most people did to solve this problem was literally have like 6 nested for loops just to figure out all these different combinations. And then from there they solved. They had a word and they checked if it was equal to these guys. Yeah. So this is a bit of a rough problem. Do you guys have any questions on that? I know John Hua and Abhinav were following, but I want to make sure everyone else is okay as well. Is everyone pretty okay with this? Any questions at all, please feel free to hop in or turn off mic or just post in chat or direct message me if you don't want to message everyone. I'm very happy to answer questions up to this point. We got one more to go. Alternatively, can I get a thumbs up if you feel like you're hanging in so far and feeling good about the problems? Okay. One from Abhinav. Okay. Awesome. Thank you, Andrea. Okay. Wonderful. We're going to move on to the last question then. Not the platinum question. Oh, they had a sleeping in class too. That's fun. Okay. Let me turn this off. Where is it? Email. Wait, no, not Silver. There we go. Nope.
No, it's problem number 2. Yeah, photo shoot 2. Yeah.
Wonderful. Okay. So photo shoot 2. This one was a little bit more difficult. In my opinion, this was probably the hardest problem, which is why I saved it for the end. Basically, the idea is we want to get from this permutation or this ordering of cows to this ordering of cows, right? The question is, how many times do we have to do this operation where we move one cow left, and we can move that cow as many spaces left as we want to. So in the second case right here, we moved this cow all the way to the beginning. And then we moved this cow, I think, back one spot as well. So we've started off by shifting the first cow forward or to the left. So we had 5, 1, 3, 2, 4. And then we moved the first cow all the way to the front. 4, 5, 2. No. 4, 5, 1, 3, 2. Yeah, and then we move the second cow in here, right? So move this guy here, and then this guy down here. So we end up with 4, 5, 2, 1, 3. Any questions on the modifications or how those are structured? I think this was a little bit of a confusing problem. So if you guys have any questions, feel free to chime in. But yeah, basically we just shift the cows, and Farmer John wants to know what is the minimum amount of times that he has to do these shifts, right? In order to get the ordering he wants. And we need to do this pretty fast. I think n is pretty big. Let's see. There's the limit. Yeah, 10 to the 5th. So we got to do this again in linear time. So we got to only look at each element about once, or only a constant number of times. Okay. So how do we do that?
So I had a slow algorithm for this, like in n squared, I think.
Okay.
So what I did is like, so you have like the first list and the second list, right?
Mm-hmm.
So if they're not in order, I would just keep striking out till they're in order.
Yeah. What do you mean by striking out?
Like, for example, can you go to the second sample input?
Yeah.
Like, for example, 5, 1, 3, 2, 4. So 5 and 5 are not in order. So just strike 5 and 5 out. And then like 1 and 1 are not in order. Strike 1 and 1 out. 3 and 3 not strike till they come in order. And then the order is just like the number of times you strike them out.
Interesting. Wait, I think I'm a little bit confused. So you're saying that we went through this first list here, and we said 5 is not in order, so we just take it out?
Yeah. You
But
take 5 out from that and 5 out from that as well.
Oh, okay.
The goal. And then like 1 and 1, you remove them off.
Okay.
3 and 3 get out.
Okay.
And then like now, like if you remove one more, wait. Let me look at my solution. Not like exactly like that. There was some other thing I did. Here, just. Oh yeah, I reduced the size of the list as well. So never mind. Continue. Let me go and like look at my solution.
Yeah, for sure. So Abhinav did a really good thing, which is looking at these partial credit things right here. Big contest tip. Always take advantage of this. The fact that they have like easier test cases. If you see this, go for points. Like I guarantee you will be happy with your solution. You'll get some extra points, and usually it'll build into the actually correct solution with a few more optimizations. So, but contest tip, if you ever see that you can get some test cases without doing anything, or sorry, not without doing anything, but you can get some easier test cases, do that because it's like free bonus points. Here, you could have gotten like 10 test cases out of 14 by doing something that was like took n squared steps instead of n steps, which is a lot easier to solve here. That said, we are going to try and do the O of n solution today. So we're going to try and get all the points. And how do we do that? So we want to know the number of times that Farmer John wants to move his cows over. And like I kind of already hinted at, we can kind of just move them. We can kind of just do it as we will, right? We can kind of just put the cows in the right position, starting from the cows that want to be first the most, right? So let's iterate through the second list actually. Let's say, okay, how do we get this cow to the front? We got to move it all the way back. How do we get this cow to the front? Well, it's already there, right? Because the 4 was shifted before it. Now, how do we get this 2 here? We got to pop that behind the 1 to get it here, right? And then the 1 and 3 kind of fall in order. So the question then becomes, how many times do you need to do this operation going from the beginning to the end of the second list? Does that make sense? So it becomes kind of like a greedy algorithm where we just have to figure out if we have to move something back at each step as we iterate through the second list. And the reason this works is because if we're moving things right to where they need to be, we won't need to do anything else after, right? So the 4 eventually needs to come here. So we might as well just do it, right? It's not going to mess anything else up by putting it there. The 5 is already going to be in its location. And then from there, the 2 is going to shift to its position. There's no reason for us to put the 2 anywhere else other than right there, because that's where it has to end up, right? And so the number of ways that Farmer John has to rearrange his cows is just equal to the number of times we have to change this permutation. Does that kind of make sense? Is everyone following so far? So we kind of, okay, cool. So we're just going from left to right. We're saying, okay, how many times do we have to move this guy back to the front? Now there's a quadratic way to do this where we can, does anyone see it? We can like just check all the other elements. So we can start off, we say, okay, I want the 4 to be here. And then I can just figure out where the 4 is in the top list by iterating through it, right? And say, okay, I'm looking for the 4, looking for the 4, looking for the 4. Oh, there's the 4. It's not in the right position. So I increment the number of moves I have to make by 1. And then I cross this out and I add it to the front of my list. And I'm like, okay, I need the 5 to be here. Turns out the 5 is already at the front, so I don't need to increase my number of moves. And I tack the 5 on. And I'm like, okay, I need the 2 to be here. The 2 is not the first element. So I iterate through my top list and I add the number of, increase the number of moves because 2 is not in the right position. Eventually I find it and I tack it on. I do the same for 1 and 3, but they're already in the correct positions. So I can kind of toss them in without increasing my number of moves. Does that kind of make sense? Is everyone following that so far? Thumbs up, thumbs down? Thumbs up, okay. Does anyone have any questions? Oh, actually, we're low on time. Uh-oh. Goodness, okay, thumbs up. I'm actually gonna pause right there. I apologize if we didn't get through the whole thing, but I don't wanna take your guys' time too much. If you have any questions, feel free to stick around after. Do you guys know when this goes to? I think it's 3:45, right? Is it 3:45? Okay. Then I don't want to keep you guys too long. But basically that gives us the 10 test cases. That actually gives us most of the test cases if we just solve that version of the problem, right? And we do it slowly. And in order to speed it up a little bit, we got to get a little bit better about how we figure out if cows are in their correct positions at that point. And we can do some fancy stuff with like pre-processing to figure out how that's the case. It's not too bad, but basically it's very easy if you just get these 10 test cases. And that's what I would tell you to do, like every single time. If you solve the first 2 problems or the other 2 problems and then got the 10 test cases with the very simple, like iterating through the first list over and over again solution, then you would have passed the contest. So, but yeah, thank you guys so much for coming. I'm going to go back to my slides now real quick. Okay. Can you guys see the slides? Oh, my annotations are still there. But yeah, thank you guys so much for coming. This is super fun. I had a good time. Thank you for participating. Sometimes it's just me like staring at black screens and that's not always fun. So I really appreciate it. I hope you guys had a good time with this contest and with the problem review. If you have any more questions, feel free to follow up with me or with Brian or anybody. I'll write my email in the chat. So feel free to reach out there. And if you want some mentorship or some practice, sign up for Breakout Mentors. We have some wonderful, wonderful, talented mentors who are, who really know their stuff. They're all like platinum and gold level. So they ran through the gauntlet, right? And they'll be very happy to help you out with getting out of bronze and achieving all your USACO goals. So quick plug for Breakout Mentors. Thank you guys so much again for coming. I had a wonderful time and have a great rest of your Sunday. I'll see you guys later. Have a good one.
Colin, can you just like I understood the n squared solution, right?
Yes.
And I read the editorial for the n solution, but I really didn't get the proof behind why the n solution works.
Yeah. Where's the, let's see, let's check this out. Okay, where's the proof? Oh, I think they can explain this kind of confusingly. Okay. Yeah, we can break this down. So let's just take this very step by step because they use a lot of like confusing variables that aren't super helpful. So if cow AI is to the left of cow AJ, that means if we have like a cow 5 and a cow 2, if this cow is to the left of the second cow, right?
Mm-hmm.
Okay. Then any modification that Farmer John performs that doesn't involve choosing the second cow, that's this one,
Mm-hmm.
preserves the relative order of cows AI and AJ. Right?
All right, that's true. Yeah.
Yes, because you're not moving the second cow, so the order is not going to change, right? Because the only cow that can move in this case is the first one, and we're only going to be shifting it left. Does that make sense?
So unless you move the two, the relative positions won't change.
Exactly.
Mm-hmm.
So because of that, if Farmer John never chooses the second cow, 2,
Mm-hmm.
that means this cow will always be to the left of this cow. Does that make sense?
Oh, okay. Yeah.
Yeah. So it's worded confusingly and they use variable names. I don't think it was smart to use variable names, and for Brown's contest, I feel like that makes things confusing. But yeah. Does that kind of make sense?
Yeah.
Okay, cool. So in that case, the number of answers we actually have is just equal to the number of cows, AJ, such that this is true, right? Such that you need to, sorry, go ahead.
So like it's just going to be the number of times you like shift a right cow.
Exactly. Yeah.
Ooh.
The number of times you have to shift the right cow. And you can do, there are efficient ways to do this. One of them is, oh, this is n cubed. I don't even know why they have an n cubed solution. Interesting. Oh yeah, so the max so far thing is just checking like the max cow that we've seen so far. And remember, if it's 5, for example, where max so far, I think, is the maximum index that a cow from here to here. So say we've iterated through all these cows, A1, A2, ... AK. And we're considering the AK plus 1 cow, right? We keep track of the maximum position across all of the first cows that they wanted to reach, right? So for example, if one of these cows wants to end up to the right of this cow, then we know that, oh, wait, hold on 1 second. Then we know that this cow has to shift, right? Because otherwise the relative order will not change, is the idea. Does that make sense?
Yeah, thank you.
Okay, cool.
Yeah.
Awesome.
I
So
came up
with by keeping track. Sorry, go ahead.
No, sorry. Yeah, I was interrupting you.
Yeah. But yeah, that's the general idea, right? Is just we keep track, we go across, we say like, okay, the maximum position that any of these cows wants to get to, we keep track of where that is. And every time we add a new cow to that list that we've already considered, so AK plus 1 in this example, we check if the position it wants to reach is less than the max position. And if it is, then the only way that the order of the cows can flip, because right now whatever this cow is, it comes before this cow. The only way that these two can change positions is if one of them changes, and so we have to increase our counter by 1. Does that make sense?
Yeah.
Okay. Yeah. So we just count that number, and keep track as we go across of the farthest position that any of these cows want to get to, and then we compare it to the position that this cow wants to get to. Cool. All right. Yeah. Thank you guys for coming. Really appreciate it. Oh, sorry, go ahead.
No, thank you.
Oh yeah, for sure. Happy to help. Awesome. All right, I'm gonna do the silver review soon. If you guys want to stick around for that, feel free. But bronze was a lot this competition, and silver was worse, man. I don't know if you guys saw the silver contest, but it was crazy.
I'm glad I didn't get the in contest promotion.
Yes. It was like, I don't know why they made it so hard this year. It was weird. I'll stop sharing. Let me check what time it is. Are you a student at Breakout Mentors, Abhinav?
Yeah,
Okay. Who's your mentor?
Nikhil.
Okay. Awesome. How's that going? Nikhil's
Yeah,
awesome.
he's really good, right? He's cracked at math.
Yeah, a lot of the guys who do math competitions end up in USACO somehow, so that doesn't surprise me. That's cool. Yeah, cool. Let's see.
Well, how hard is the gap between silver to gold? Because like I got promoted to silver this time, so
Nice.
how hard is it to go from silver to gold?
Yeah. Well, first off, congratulations. That's a huge achievement. I think a lot of students don't make it past bronze anyway. Like the skew is very exponential in that sense. And for that same reason, the gap between silver and gold is very big. I think bronze and silver is a lot about like coding fundamentals, and you're kind of thrust into this world of problem solving. So it takes a little bit to figure out how to solve problems fast. And that's once you get that, that's how you get out of bronze, right? But then the silver to gold jump, that's when you have to start learning algorithms, right? You take the coding knowledge you've acquired, and suddenly you have to also implement all these difficult concepts. So yeah, I think the main gap there is entirely different, where from bronze to silver, it's a lot about programming and problem solving. And from silver to gold, it's a lot about like studying and understanding these new concepts and algorithms in order to advance, and how to apply them, obviously. But yeah, so I think the gap is different, not necessarily comparable, if that makes sense.
Yeah.
But I'd encourage you to try if you're into it. It sounds like you are. So yeah, very fun stuff.
I'm just hoping to like clear silver in the December contest, which is coming. Yeah. Because like I did like some of the USACO guide silver stuff, and like awesome. in that it seems like it's just a direct implementation of the algorithms, but I know that true in the coming contest, right?
Yeah.
Like, it's definitely not like in the past contest, it was just like direct implementation, but now it's rigged up a bit.
Yeah. It gets a little harder. What did you think about the concepts in USACO guide?
They were fairly easy, I would say.
Okay. Which ones have you used so far?
DFS, then flood fill,
nice.
prefix sums.
Okay. Cool stuff.
Like I think we have to go into coordinate compression and like 2 pointers, I guess.
Yeah. Yeah, it's yeah. I mean, if you find it easy, that's awesome. I would caution, because I think part of the hardest thing is like applying those concepts. Like you see the concepts and you're like, oh, I know how to do this. This is cool. This is intuitive, right? And then you look at a problem that's supposed to be solved using it. Like, wait a second, how do I apply this, right? Or how do I even recognize that I need a concept here? But yeah, really cool that you're getting into that stuff. That's awesome. I think I'm going to close this chat because I got to go to the silver review session. But thank you guys.
Is it in the same like same Zoom link?
I think it's another one, but you should have gotten an email with both of them if you want to join. So
okay, right. All right. Thank you.
Yeah. See you guys later.
Bye.
Bye.